So a lab that we do in honors is we actually have them, here it is, right here. We actually have them derive the mirror equations. But we don't use the lens maker equation, or the mirror maker equation, I guess. The if I do, I die. 1 over f equals 1 over dou over 1 over die.
Does everyone know that equation, or does anyone not know that? You don't know that? Okay, there's a, most textbooks, I'm going to erase this clip. You still think?
Oh, yeah.
For curved mirrors, and here's the focal point, that's the focal length there. They have the relationship between, if I have object here and image there, this distance would be the object distance. And then, sorry, am I going too fast here? And here, of course, is the image distance. And the relationship between these is if I do, I die. Now, can you imagine students trying to derive this? If you're designing a lab where they actually get the mathematical relationship, this would be really, really difficult. So
it's even difficult to work. In regular we give them that equation. We tell them to make up 2 numbers and solve for the third. Wow.
Yeah. They just need.
Well, we have to make up f in one of the do, like do. We have them solve for di, and that's tough,
right? Not putting
down
the kids.
1,
yeah.
But yeah.
Not putting down the kids. That's just for whatever reason. Once you're outside of the math class, it's very difficult to do. But Bruce and many people, I think this might be the PSSC way. Scott, you probably do the Newtonian method. So Keith's going to go about doing how we. Do you want me to draw?
Sure. Yeah, go ahead. Say diagram. So we just give them a concave mirror. We were going to have you guys do this lab, but we realized that after 2 hours we were a quarter way through the work, so we're not going to have you do it. And then we created these little light bulb sets. I think you can buy big ones of these, but they were real easy to make and real cheap. And it's not a very bright light bulb, but it's bright enough. So we run a piece of paper tape along here, and then I need to use this piece of paper. What we have them do is, with the object there, the lights aren't too bright. You're going to be. Well, can you use your black screen again? And I'll shut this door. There it is. Now I see it. Alright. This might be hard for you to see, because I'm standing in the way. But do you see that little dot of light right here? Yeah. So that's the image. That's the image of the light bulb. And if I move it, oh, actually it got better. You can see it starts to get blurry. Perfect. And then I move it, it gets blurry again. So you can actually find the location of the image. You move the object, and when the object moves farther away from the mirror, the image moves closer to the mirror. Vice versa.
Now, for this classroom, we have to put black plastic across those windows. So we've got for about a month black plastic, because this is way too much light.
Right. But we actually have them go through and collect, I think, 16 data points. Okay, the mirror star is right here. And of course, we have them find one of the most important points where the object and the image are at the same location. And that would be the 2F spot, right? So once they've done that, they can then, well, they have to measure differently. So in the lens maker equation, as it's called, they measure everything from the mirror. But what we need to do for the Newtonian method is measure everything from the focal point. So they call them different letters. They call them SI and SO, where SO is the object distance, and SI is the image distance. F is the boundary between what I call the positive lane and the negative lane. And nicely enough, I do want to show the equation before.
Yeah, let's. So now, if we get the virtual images, we have to go to my computer now.
Yeah.
To get the virtual images, remember the parallax that we talked about before? To actually get them to take data, that's why we teach them parallax. Is now when the image is behind the mirror, they're placing another object back there. And again, we use just a nail now instead of a light bulb because the light's not going to get there. Put a little nail in front, and then they have their partners place a nail where the image is. Now again, you can measure your data. For regular physics, we're not so much interested in modeling data yet, from getting equations from data. So we do just a qualitative lab in the regular physics. I'm going to talk about that next. Is this the both labs are on the CD, the honors physics lab and the regular physics lab. And this is the data. This is student data. I just typed it in just while you guys were making your demos.
I asked one of my students, one of the good ones, that still has all this stuff. Hey, can I borrow your data? And this is actual student data.
Now they plot it by hand, but I just plotted it in Fathom.
And then again, they go through straightening the graph.
Want to pull that upwards?
Yeah.
The nice thing about does anyone use Fathom? It's it started out as statistical software, and it's really. Does anyone have Fathom at their school that they know of?
Just like
Let me show them.
Excel, it's like Excel.
But
It's better.
It's a lot nicer than Excel. Oh, this is so big, huh?
Yeah, you can.
You giantified everything. Yeah, I was trying to.
Oh yeah,
that's
yeah, you can see there's also been some good things. You can talk about like the outlier points. These points at the extreme, it's going to be a lot harder to measure. So those ones you wouldn't include in your best fit line. Your data table, huh? Can you show data tables?
I can't. Let's see. Because it all went giantified to put it on the screen. No big deal. All right,
There it is.
Oh, how'd you do that?
I don't know. I use the PowerPoint, obviously.
Yeah, that did. You can drag what we to create graphs. Let me just delete this graph. New graph. You just drag it to the screen anywhere you want. Whatever you want to plot on the horizontal, drag it there. Whatever you want to plot on the horizontal, drag it there. Yeah. Okay, now, actually, our regular physics and honors physics students, they don't use this. The AP Stat students do. For AP this year, I said, if you want to use this, and then, I'm finding out things that never knew existed on.
So look at that. And once you type the like on the data table, it's got centimeters on each number.
Yeah.
And it just threw them in on the, you knew to put them on as units.
Right, you can put units.
Hey, is that a district software program or is it yours?
No, it's district. So.
It is district, so I should find my computer then.
Yeah.
Absolutely, yeah. Oh, yeah.
Yeah,
You get
Steve
free.
teaches in the district, in our district, so he can, Steve, right?
Yeah.
Then we created
Not
just
yet.
a 1 over SO. They go through the process of realizing here if you double SO, what happens to SI, and it's an inverse relationship. This, I wonder if I can, let me get rid of this line here. It's really nice. Can I delete this line? This particular line here is movable, and I locked it at 0, 0. There's just an option to lock it at 0, 0. So I just went through visually, which is what we have our students do. And tell me when to stop.
There.
About right there. At the bottom, I wish you could see this. Well, here's what we're going to do. There's a reason for this. And I want SI here versus SO there. And I want to add the line. And I want to lock intercept at 0. We'll go through the same procedure. Do you guys see the what's down here? So it gives you the equation of the line, including, no math program will do this for you, right? Yeah, including the units, and the units done correctly, so it's centimeters squared. Now we've got a slope of 393 centimeters squared. And
Let's call it 400.
It's called 400.
And if we look on our little boxes, I think we got these from Educational Innovations, super cheap. The focal length of these mirrors is 20, which is pretty nice because then it has a nice relationship. When we actually have them do this, we take the square root of their slope, and they've already found the focal length ahead of time. You got it.
Square root of 400 is 20. Yeah, I mean the data is really, really nice.
So therefore, m is going to equal to f squared, right? And so we get our nice equation, SI equals f squared SO to the -1 plus 0, which then comes down to SI SO equals f squared, which is, it's the same idea as this equation. It's just an equation that you're able to derive and go through the actual mathematics and use a lab to come up with it.